We're almost done with chapter 6. We have about 2 days left, and then we'll be finished with it. We can move on to a whole new chapter. This is going to be 6.9. There's actually 2 days of this. It's called complex numbers. So what is a complex number? So here's a definition. It's not really that bad, even though it's called complex. A complex number is a number of the form a plus bi, where a and b are just real numbers, and I, as you know, is the square root of -1. So the reason they call this complex is because you have like a real part and an imaginary part. The real part is just a, so this will just be a number in here, a, and then the imaginary part is the part that has the imaginary number with it, bi. So here's some examples here. If a plus bi is 3 plus 4i, what is the value of a? What is the value of b? So you're kind of comparing it to these two here, right? A is this number by itself, so that would have to be 3. So we could say a is 3, and b is a number in front of I, which is 4. Pretty simple. There's actually a way to graph these if you pretend that the y-axis is imaginary numbers and the x-axis are real numbers. You can graph this by kind of going over 3, 1, 2, 3, and then up to 4i. And that's a dot here. We're really not going to be graphing these. That's more along the lines of some further mathematics courses, but not going to be doing it here. Example 2. This one asks a different question. So notice here we have if a plus bi equals 4 minus 2i, what is the real part and what is the imaginary part? So now you kind of have to go back up here and look at what it means by real part and imaginary part. Really, the only difference is we're going to identify the imaginary part where we include the I. So in the first one we did a equals 3, b equals 4. Now we're going to do what's real is just the number by itself. Real is 4. The imaginary part is going to be, so this is the real, 4. The imaginary part is this part. So I'll say it's negative 2i. Pretty simple. You're just identifying what it is. And if you were to graph this, you would go over 4 on the x-axis and down to negative 2. Again, we won't be doing graphing, but that's just an example. Example 3. If a plus bi equals negative 4 plus the square root of negative 3, what is the value of a and what is the value of b? So again, we want to make this look like a plus bi. Right now we don't have an I here, so we're going to have to make one. So we have our a value, which is negative 4, but we need to work with this a little bit. If we remember, you can do negative 3 as negative 1 times 3, and then split it up that way as two separate square roots. So that would be the square root of negative 1 times the square root of 3. Now, square root of 3 is going to be a decimal because it's not a perfect square. So I'll leave it like that. And then the square root of negative 1 is, as we know, I. So this is I times the square root of 3. I'll bring down the negative 4. Negative 4 plus. So here's really your answer. And so if we're going to ask the question of what's a and b, a is going to be the number by itself, which we already knew. So we'd say a equals negative 4. B is the number in front of I. In this case, it's behind I. B would be the square root of 3. And believe it or not, there actually are quite a few careers that use complex numbers. Here's just some examples down below. But you can look them up yourself and figure out what uses complex numbers. Sometimes we actually will do like a little project on that because it might seem like it's a fairly useless concept, but it's actually used quite a bit. Okay, so there is a huddle for you to try. It's pretty simple. You're just doing the a and b values of what you have here. And then we're going to move on to something a little different. So again, whenever you put these together, just think about i's as being regular variables. So we're going to think of these as just being real numbers instead of imaginary when we add or subtract complex numbers. As an example, if we're going to do 2 plus 3i plus 6 plus 9i, we're just combining like terms, right? That's all we're doing, combining like terms. I'll write it out. Like terms. So what do we have in common here? We can put the 2 and the 6 together to get 8. 3i, 9i is 12i. So for some reason, when we do complex numbers, they always have it here, like with the real part first, a 8, and then the imaginary part second. So it always goes real and then imaginary, which is kind of weird because we're used to putting the variable stuff first, but that's how they write it out. Real part, then imaginary. It's also kind of how you know it's imaginary, not just using a regular letter for I. Example 2, put these together, we get 4 and 7. Add them together, you get 11. Negative 3 and 5 would be a negative 2i. And that's it. Number 3, we can distribute the negative 1 here. Be careful with that. You have to distribute the negative 1 to each thing here. So I'm just going to rewrite this one out. So we have negative 2 plus I minus 7. So both of these are going to turn negative. Minus 9i. Combine like terms, negative 2 and negative 7 is negative 9. 1i minus 9i is negative 8i. There's your answer. Every single time you do these, you're always going to have in the real part and imaginary part. It'll always look like this. A real number and then your imaginary numbers. There's another huddle for you to try. 4 problems there. Don't forget to distribute the negatives in some of these before you combine them. The next part to this is we're going to start doing multiplication. So when you do multiplication, you're going to do distributive property like we do with anything else. But there is going to be one additional part to this, which you'll see in a second. So put the following expressions into the complex number. We're going to look at a plus bi form. So it's going to look like this in the end, even though it may not seem like it as we do it. So for example, if you have 4i times the quantity 8 plus 5i, we can distribute the 4i to both things. You're familiar with doing this, just as if it were an x. So 4 times 8, we get 32i. 4i times 5i, it would be 20i squared. So I don't know if you noticed, but this does not look like the a plus bi form because we're not done yet. The reason we're not done is because we know what I squared is. We can do this part right here. If you remember from a while ago, I squared is the same thing as negative 1. So this will be a pretty key thing that we have to remember as we do these problems. So every time we see an I squared, we're going to replace it with negative 1. So instead of writing this as 20 times I squared, it can be 20 times negative 1. And we still have this 32i. Now we can't do anything with 32i. That has to stay like that. But now we can basically just rewrite it into the correct form. A plus bi, we're going to put this. This is actually the real part now. It's 20 times negative 1. So it's going to be negative 20. I'm going to write that part first. Plus 32i. So now it matches up to this form up here. Example 2, again, distribute. We'll get 63i minus 42i squared. And again, as you do these, you can pretty much just maybe even do this in your head. I squared turns to negative 1. We're going to get I squared quite a lot. So it becomes negative 42 times negative 1. This will turn into a positive 42, so I'm going to put it at the front. And 63 is also positive, so there's our answer in a plus bi form. Just looking through how much we have left here, trying to finish it. Okay, for example 7, again, this is kind of like distributive property, but we're going to do it twice. And again, we're always going to put it in this form. So this is the one we had to do the arches because you're multiplying them together. So we have to do this arch, which would be 24. Then 6 times 7i, 42i. Then we got to do it with this one, negative 2i times 4, which is negative 8i. Negative 2i times positive 7i, which would be minus 14i squared. So just like we've done this before, we can combine the two middle terms, and then we can also change out I squared to negative 1. So I'll do that at the same time. We'll have 24 42 minus 8, that's going to be 34i. And then we have minus 14 times negative 1, because again, changing I squared to negative 1. So I don't know if you noticed, but now we only have two numbers with no variables, and then our number with a variable here, 34i, is going to be what goes on the end. So this becomes positive 14. 24 plus 34i plus 14, if you multiply them together. And now we can put this with the 24. So that's going to give us 38 plus 34i. Again, the final answer looks like this form up here. It's going to happen every single time, mostly because we get this I squared every time. All right, try another one here. Multiply these together. We're going to get 5 times 6, which is 30. 5 times negative 2i, negative 10i. Then multiply these two. 7i times 6. Oh, we're going to get 42 again. So 42i. 7i times negative 2. Again, we get negative 14i squared. So some of the stuff looks similar to the other one we just did. Combine these two in the middle, change I squared. If you want to and you know how to do it, you can just change I squared right away. And we say, okay, this is just negative 1. Or you can go even further and say, it's going to change this whole thing to a positive 14. All right, so we have 30. Put those two together, you get plus 32i. And this will become plus 14. Combine the first and the last. They don't have i's anymore. That would be 44 plus 32i. I'm hoping overall this isn't too bad. We're really just looking at one extra step where we can simplify the I squared. We haven't had any higher powers than that, though. Okay, so there is a huddle for that one as well. So we have 3 huddles in. Now we're going to move on to expanding radicals. The only difference between these problems and the other one, which I think I'm eliminating this one. We don't need to do this one. Talk about that maybe later. We're only going to do these two here. I know it looks kind of difficult, but we're just going to simplify the square roots first before we try multiplying. So for example, this would be 5 plus the square root of negative 16, if you remember, would be 4i. I should probably fix that here. Put plus here again. And then this one would be 2 plus the square root of negative 9, which is 3i. So now we actually have a problem that we just did back here. You know, we have i's in these positions, and so it's no different. Where we can do the arches and finish it off from there. So let's go ahead and go through that. 5 times 2 is 10. 5 and 3i is 15i. 4i and 2 would be 8i. 4i and 3i would be 12i squared. Now remember, this turns to a negative 12 because we have 12 times negative 1. Put these together, we get 23i. And we just got to add the 10 to this. Looks like that we'll get negative 2 plus 23i. There we go. Part B is done the same way, and then I think we have one left to try. One new section left. Then we'll be done. So this one you can rewrite. We have negative 1 plus the square root of negative 49 would be 7i. And then the square root of negative 64 is 8i. Now we'll distribute. Negative 1 goes to both. That'd be negative 6. Negative 1 and negative 8 is positive 8i. And then we do the 7i to both of these. That would be 42i. And 7i times negative 8i, which is negative 56i squared. Okay, we'll put these middle ones together like we've been doing. That's 50i minus 6 here comes down. This will become a positive 56. I hope you can figure that out by now. That just changes the sign. I squared goes away. Put the first and the last together. We get 50 plus 50i. Again, these two are not like terms. You do not have a variable in both of them, so you can't put them together. It does not become 100i. Okay, so you have a mastery to do, 2 of those problems, and then we'll move on to the last set. Simplifying radicals. So we're going to simplify these radicals completely, but we're not going to actually have decimals. We're going to do this by hand for the most part. I guess you can use a calculator to figure out some of these perfect squares. So what we need to do is look for perfect squares in these numbers, because if you do the square root of 50, it's like, let me think, it's 49 is 7. So it's probably like about 7.1 or 7.2 or something like that. I don't want to do decimals though. Instead, what we're going to do is find the perfect square that's in 50. Now, when I mean perfect square, I'm going to write them out real quick, at least a couple of them. Perfect squares would be like 1. 1 times 1 is 1. 2 squared is 4. 3 squared is 9, right? We can keep going. 16. Another perfect square would be 25. 5 times 5, 36. You should know these out to at least 10 or 12. Then it goes, that was 6, right? 7 is 49. 8 is 64. I'm going to at least go up to 10. 9 is 81. 10 is 100. And you should know 11 and 12, 121, 144. I'm not sure if we'll see anything higher than that. Most times we'll see the ones down here. So what you can do is you can take 50 and you can just start dividing them by these numbers. Or you might be able to figure out how 50 can be split up into two different numbers. And one of them has to be a perfect square. I don't know if you noticed, but 50 can be nicely separated between 25 times 2. So I'll show you how we do this. We're going to write this as a square root of negative 25 times 2. So I'm going to put the perfect square with the negative number, because then I can do what we've done before in the last class. We can split this into 2 square roots. And this one we can do, this one we can't do. The square root of negative 25 is 5i. Times the square root of 2, can't do anything else. That's your simplified answer. Let's move on to number 2. It's really not that bad. You just have to figure out, which number to use up here that works to get 72. So how can we split 72 apart? I have to use one of these numbers. I think it is 36. 36 times 2. So I'm going to split this between negative 36 times 2. And again, I'll split the square root up. I don't know why I made a big one then. Square root of negative 36 times the square root of 2. And if we square root this, we're going to get 6i times the square root of 2. That's a simplified version. And by the way, if you did put this in the calculator and got a decimal, like I said here, this would be like 7.1 or 7.2i, right? First off, you can't put the negative in there because you won't get the right you won't get an answer. But secondly, if you do it down here, 5i times the square root of 2, you would get the same answer, hopefully. It's just a more simplified version with no decimals. What it says here, no decimals. All right, number 3. We're going to do 2 more, and then you have, I think, 4 to do as well. I'm going to do 4, and you do 4. And then we'll be done. Okay, square root of negative 45. I'm looking, again, for a perfect square. If you don't know how to do this, just take 45 and start dividing by these numbers. Once you get a whole number, you'll know what to use. You don't have to go too far with this one. I think 9 works. 9 is a perfect square, so I'm going to separate this into negative 9 times, how do you get 45? That would be 5. So square root of 9 we can do. Square root of 5 you can't do. Square root of 9 times square root of 5. If you want to skip this step, that's fine too. You could probably just go on to the next one. So this would be 3i square root of 5. All right, last one. I'm trying to figure out how to get 80 or negative 80. Let's see. 8 and 10, but neither of those work. So you might have to go through and actually divide them to see. I'm going to say if you divide these here by, 80 divided by 1 divided by 4, 1 would be useless, so I don't think we're going to use 1. 4, 9, I think 16 works. 80 divided by 16 gives you 6 times 5. Negative. So I'm going to go ahead and throw that underneath the square root. So the square root of negative 16 times the square root of 5. Oh, we already had 5 over here too. Square root of 16 is 4i. There's negative in there, times the square root of 5. That's your final answer. So really, the only difficult part, I guess, is trying to find what perfect square to use that makes up the number that's inside the square root. Because whenever you split it apart, if you were to multiply them back together, you have to get this number that's inside the square root. Because 16 times 5 is 80. Okay, that is it for 6.9 day 1. There is a day 2 that we're going to do later, but that should be enough for day 1. And hopefully it wasn't too bad. You can go ahead and finish the warm-up and the rest of the huddle and everything else. The huddles and the masteries.